Imagine what would happen if I counted to 3 and then released this phone. It is probably very easy for you to predict the outcome, and you might even advise me that it is not a good idea. This is what physics does. It helps us to explain and then to predict the world around us. In the 17th century, Newton derived the theory of gravity, which described the force acting between any two objects with mass. The Newtonian gravity is sufficiently accurate for many practical applications. However, over the years, we have encountered observations that the Newtonian gravity cannot explain, specifically for objects that are very massive or move with high velocities. This discrepancy motivated Einstein to derive a new theory of gravity, called general relativity. This is how we advance our understanding of the universe. When our current theories can no longer explain observations, we need to correct them or derive new ones. Today, general relativity is the best theory of gravity that we have. Even so, we want to find deviations that might lead us to a more fundamental theory. To achieve this, we study systems in extreme environments where gravity is so strong. So where do we find systems that move with high velocities or that are very massive? So welcome to my world of black holes. When you think about black holes, you probably imagine something like that.
All right, class, today we're learning about black holes. Now the thing about... Everybody grab onto something! Okay, class, how about we learn about the sun?
However, the study of black hole is a serious subject. In 2020, the Nobel Prize in Physics was awarded for the research of black holes. But what exactly is black hole? A black hole is a location in space-time where the gravitational attraction is so strong that nothing, not even light, can escape from it. The surface of the black hole is known as the event horizon, which is the point that not even light is fast enough to get away. Once matter crosses the event horizon, it can only move inward, toward to the center of the black hole. General relativity predicts that astrophysical black holes can be completely characterized by only two properties, only by their mass and their spin velocity. Any other information about the black hole, about the matter that formed the black hole or is falling into it, disappeared behind its event horizon, and it's no longer available to external observers. So we cannot see what happens inside the black hole. So how do we know that there are black holes in the universe? How can we observe them? Do you remember the 2020 Nobel winners? Two of them are observational astronomers who discovered the supermassive black hole at the center of our galaxy. But how did they know that there is a black hole there if they could not see it? If you will go to a dark place to watch the stars, you will be able to see this beautiful image. This is the Milky Way, the galaxy that we are part of. The Nobel winners developed a method to watch to the center of the Milky Way. At the center of it, they found a dense cluster of stars known as the S-stars. They closely monitored their orbit over 20 years, and you can see their observation in that video. If you will closely monitor their orbits, you will, especially that of a star named S2, you will see that they orbit around an object that is not visible in the observations. By analyzing the orbit of S2, they determined that the mass of the invisible object is huge. How big the mass of this object? They found that its mass is 4 million times the mass of our own sun. The only plausible explanation for such an object was a supermassive black hole. The orbit of the S-stars were the most direct evidence for a supermassive black hole in our universe. But what if I will tell you that we can see this black hole? This is a real image of the supermassive black hole at the center of our galaxy. But how is it possible? We cannot see what happens inside the black hole because it is completely dark, but we can observe the emission from the interaction with its surrounding. So in that picture, you see the gas surrounding a dark central region, which is the black hole. Given that the black hole is 27,000 light years away from Earth, its apparent size on the sky is similar to that of a donut placed on the moon. So to capture this single image, the Event Horizon Telescope project combined data from a network of 8 radio observatories across the planet to form a single Earth-sized virtual telescope. It took 20 years to determine the mass of the black hole. The next 20 years will be used to measure its spin and to test general relativity. But there are some astrophysical sources of noise that can make this test a bit problematic. In my previous research, I derived a method that removes some of these astrophysical noises and may make the future measurements a bit simpler. So far, we have discussed two methods to observe and study black holes. One of them was using the movement of stars around it, and the second was using the matter around the black hole. The third method that we will discuss today is by the death of a star. When a star gets closer to a black hole, it is stretched in one direction and compressed in the other one, until it gets to a point that it will get torn apart by its strong gravity. A portion of the material from the disturbed star will eject into space, while the other part will form a disk of gas. This is known as a tidal disruption event. We cannot see those events in high resolution as you see in this video, but we can detect the radiation from the gas involved. We know that at almost every large galaxy, there is a supermassive black hole in the center. So to detect tidal disruption events, we need to focus on the center of galaxies. Therefore, several telescopes continuously survey the sky to search for any change in brightness at the center of galaxy. Once such of these changes is detected, we can track the luminosity over time, and if the observed event is a tidal disruption event, we will see a significant increase in brightness that can outshine the host galaxy for weeks or even months. In the plot I'm presenting here is an example of an observation for a tidal disruption event, which shows an increase in brightness, followed by a gradual decay until it's flattened over time. To study these events, we, as theoreticians, develop mathematical models that try to understand what are the pieces of physics that can explain the observations. Once we have a mathematical theory, we can generate the predicted luminosity over time and then compare them to observations. But the ultimate goal of such a research is to accurately measure the black hole parameters and then to test general relativity. But as we keep the research, we find that that our theoretical models are not perfect, and we still have many astrophysical uncertainties. In my research, I study how magnetic fields can change the theoretical models and whether they can explain the observations better. In that plot, I show the predicted luminosity over time for two different theoretical models. The curve in blue is the theoretical model that is commonly used, and the curve in black is a theoretical model when I added magnetic fields. And you can see that the results are really different. In conclusion, general relativity is the best theory of gravity that exists today. But we still want to test it, and it is not the final theory. To further test it, we need to study systems in strong gravity around black holes. And today, we talked about 3 methods to do it. In the future, the new theory will hopefully become a common knowledge that will help us to understand our world. And for you, to advise me to not drop my phone. Thank you very much.